Welcome to Breadboarding. In this video I'm going to be summarising the Breadboard PC project as it currently stands, which has been developed over the last 36 videos. If you want to see more detail on this, then go to the playlist and look at the Breadboard PC playlist, and then you can go through the videos one at a time. Each one's about 15 to 20 minutes and it will take a while to get through it all. This will actually lead you through building up this computer from the very basic first breadboard all the way up to the current working system. So what's a solderless breadboard? So this is an example of just one of the breadboards that this project is using, and on here you can see, if we just get the light right, this is an Intel 8088 microprocessor from about 1983, this particular one is. Now this particular computer makes use of about 15 of these size breadboards, and what we've also done is the power strip. So this is an individual power strip, and if we join these together we can make these into data and address buses, and so what you've got here is a number of address buses along the board here, and that's how we've made this project so far. So let's power this on and see if we can run up PC-DOS 2.10. So this comes up in the Nanocomp Monitor, and I'll explain a little bit later exactly what this monitor is, but this has allowed me to develop the system so that I can debug it and get the BIOS working before we actually manage to boot MS-DOS or PC-DOS. So we're just gonna pop in the floppy disk into the drive here, and in fact we just need to press B for BIOS or boot, and what this is going to do is to display up on the screen. So we've got the video capture card here. I'm just going to show you the system booting up and hopefully booting MS-DOS or PC-DOS. Just press B. The little tune with the BIOS plays just when it comes up. You can now see it's testing memory, so we've got about 512k of memory here. We're just going to put in the date, so that would be 06/01/2024, and the time is 21:05. So if we just check version and do dir/w, there we go. So we can just do, let's tidy this up. Now I've not got much else on the disk here, but it just shows that we've now actually got PC-DOS 2.10 working. Let's see what happens if we put in a Windows 95 floppy disk and boot it again. And this says that we have to have a 386 or better to run Windows 95, which is what we'd expect, but at least it shows that it's able to read the Windows 95 DOS 7 boot disk. So let me take you through a high-level explanation of the board layout you can see here. So there's the lower half here. Now this is really what was necessary to produce the original Nanocomp compatible computers. So this is the Intel 8088 version of the original 6809 Nanocomp project that I did. So you've got here the Intel 8088 CPU and the supporting clock and buffer circuit. Now the 8088 needed more chips to support it than the original 6809 did. Then we've got the address bus area here, which are just the two wide power strip connectors joined together. We've got the data bus. The address bus is 20 lines, that's A0 to A19, and that allows 1 megabyte of memory to be addressed by this CPU. Then we've got an address decoder that determines when the RAM and ROM is accessed and the various other chips. Then there's a serial port and a parallel interface adapter, and that's used to drive the LED 7-segment display and keypad. Then there was a Monochrome display adapter video controller developed. I'll explain more about that. And it is also capable not only of doing mono, but also can do some basic colour, but in hex mode only. Then on the second half of the board, at the top half, so these are all the sections we've already covered. One of the things that I've covered in the breadboarding tips videos is the power distribution, and one of the problems when you're putting together a larger project like this, if you just daisy chain the power between each of the boards, then by the time you get to the bottom left hand corner you'll probably find it'll only be about 3.5 volts rather than 5 volts. So you can see here I've got little voltmeters around the place, and generally I try and keep these above 4.75 volts. There's quite a lot of effort goes on to try and make sure the power distribution is good throughout the board. These are Breadboard Buddy PCBs from Tindy. Then a PS2 keyboard and mouse controller. At the moment we're only using the keyboard, we'll be adding the mouse in later videos. A lot of the PC compatibility side of things is handled by the parallel port interface, the power on self-test port, so this is how we can actually get status information from the PC as it's starting up, the programmable timers and interrupt controllers, and the DMA controller, the direct memory access controller. Now this is necessary to control the floppy disk controller and also early hard disks, but this was the area that I've had by far the most trouble, and I'll probably do a video specifically on DMA controllers sometime in the future. So the Breadboard 8088 PC project is part of the Breadboarding Labs site. Now I set up the Breadboarding Labs channel in August 2022, and what I was trying to do really is building reliable digital electronics projects at a scale perhaps that most advice would advise against. The important thing about this is using good quality breadboards, and I've followed very much Ben Eater's videos on building his own microprocessor. I'd recommend you look at Ben Eater's videos if you're considering building complex breadboard projects. Now the Nanocomp 6809 project was the first one that I started on. That was back in August 2002, and the Breadboard PC project started in December last year. So this is one of the final pictures of the Nanocomp 6809 project, and this is based on a 1981 Wireless World project, so Wireless World magazine. And if you look in the playlist above and see in the description below, then there is a playlist that takes you through all of this. So again, similarly, we've got the 6809 CPU clock and buffers, the ROM, RAM and address decoder, the serial port and parallel port for controlling the 7-segment display. We've got our power distribution, and then we've got a slightly more complex video controller here that was able to do both text and graphics at MCGA mode compatibility. So this is a graphics mode very close to VGA. Then there's a PS2 keyboard, sound and joystick controller, and finally added a 2.5-inch SATA IDE drive with a converter on it with an IDE hard disk controller. So these were the original January and July versions of Wireless World magazine, where the Nanocomp was first introduced, and in the July edition they updated the original 6802 design to actually cover the Motorola 6809, which was a fairly recently released. Now the original design was very straightforward. There's only about, I think, 8 or 9 chips here. So we've got the processor itself, the ROM, got 2 RAM chips here making up 1K, the address decoder, the peripheral interface adapter, and then 2 driver chips for the LED and the keypad. Now the 8088 version needs additional latches and bus controller, so you need a few more chips to do the 8088 version of this. Now during the Nanocomp project, in addition to building out the hardware, I also managed to develop a number of programs. So in text mode I managed to get a Tetris game working. Then in the black and white 640 by 480 black and white mode we managed to get a Lunar Lander game working, and this is actually a screenshot from the working program. Then finally with the high color graphics modes, this is 256 color graphics, then I was able to actually get the original Doom startup screen logo to run on this. It's not capable of running Doom because the processor is way too slow. It was capable of showing the Doom startup image. So the IBM PC was released in October 1981. Now it used the 8088 version of the Intel 8086 processor. So this has an 8-bit data bus to the outside world rather than the 16-bit data bus. And although the number of pins on the chip were the same, the 8086 required a 16-bit data bus and was a lot more complicated for wiring up on breadboards. So we're using the 8088 here. Also made it cheaper for the earlier computers as well. Now there are a number of 8086, 8088 breadboard projects out there, but I don't believe there are any which are actually PC compatible. And there's a link here of one of the main ones that I was looking at. I think that's Slaydor's. Now the breadboard PC we're building is a PC XT hybrid, so it's not the original IBM PC from 1981. The XT came out in 1983, but it does include a number of generations of components, and part of the reasons that I'll explain on the next slide. So we're going to be running an early version of DOS, so either MS-DOS 3.3 or PC-DOS 2.10, which we've already shown. For the video, we're going to be using Monochrome display adapter, and I'll talk about that in a few minutes. We've got some parts from the original PC and PC XT, but then there's bits from the PC-AT from 1984, so the real-time clock and dual interrupt controllers to allow more devices such as mouse and network cards. A lot of the additions were the IBM PS2 additions for the PS2 keyboard and mouse, the 3.5-inch high-density floppy disk drive, and the MCGA display adapter is a sort of crossover between the earlier CGA and VGA video adapters. And then finally, the hard disk drive is an IDE disk and controller from around the Compact Desk Pro 386 era, about 1986. So this is a photo of one of the original IBM PC prototypes on a wire wrap board. So this is the top side of the board, and this is the bottom side. So this is just the basic RAM, ROM, bus controllers, all that sort of stuff. There's no floppy disk video card or anything like that on that. So when we're actually comparing the layout of that board on the bottom there with the current breadboard PC, then it isn't actually quite so bad. And if you also think that this board here, in addition to what was on the previous page, also has the video controller and the floppy disk controller, which weren't included on the previous board. So in the early videos, the first stage really was building a Nanocomp 8088. So this is effectively trying to reproduce the 6809 project using the Intel 8088. This covered the first 12 videos or so in the series, and there was the first summary video actually covers all this side of things. So I'm not going to go into in a great level of detail. I'll include the summary videos in the description below. Then moved on to build out the Monochrome display adapter video controller. Now this covered quite a few videos, so that's 13 to 21, and there's actually summary video 2 actually summarizes that. So if you don't want to go through all 36 previous videos, then if you do the first summary, the second summary, and this video, then you should have covered all the 36 videos so far. Then since that, then we've been building out the PC compatibility, the power on self-test port, interrupt controllers, timers, and the parallel port, adding the BIOS and changing the board to add wait states where it's needed so that things don't happen too quickly, adding the PS2 keyboard controller, which is also the mouse controller, direct memory access controller, floppy disk controller, and then we tried to get this to then boot and run DOS from floppy disk, which was quite challenging. There were a number of issues needed to be addressed, in particular around the DMA controllers. And then we also then, following the release of the MS-DOS 4 source code by Microsoft, then we also then built our own version of MS-DOS, and we're going to be using this to actually debug the boot up process in some future videos. Now the plan I have at the moment is, once this phase of the project is over, then we're going to go on actually really build out the PC to add the real-time clock, a hard disk, boot DOS from the hard disk, add a color CGA video controller and enhance it to the MCGA level, which includes the VGA graphics modes. Then we're going to be getting the PS2 mouse running and seeing if we can get an early version of Windows. So I'm hopeful of getting Windows 1 and Windows 2 running, and possibly Windows 3. Then depending on how that goes, they'll see whether we can add any internet networking, network adapters and sound cards, those sorts of things. Now, before I started on the project, did a lot of background reading. I should say that the IBM technical guides for the original PC and PC XT were excellent, and I've used those and referenced those a lot in the videos. So if you look at any of the videos, you'll see that I reference those documents quite heavily. But this 88 project book was by Robert Grossblatt and had quite a number of laws of life and design, which I found quite amusing. So I think the key thing really on all these sorts of things, and anyone trying to do this type of project, think for yourself. Don't just take the information that other people have given you or that companies have published as completely accurate, because sometimes there are problems with it. And a couple of the key things I've pulled out from when I originally did this slide, the things that probably resonate the most. There's no substitute for a datasheet. It's always worthwhile rereading the datasheets several times when things don't work, because quite often there are things buried in there that you missed the first time through. The other issue is I'm now on my 5th DMA controller. If you can't afford to blow it up, you can't afford to use it. Fortunately, these DMA controllers were quite cheap, and it's more important to get it working than to get it perfect. You could spend an awful lot of time trying to get the ideal board layout, trying to get everything absolutely perfect, but really getting it working is more important. And one of the things I did start in the first or second video, a circuit of 1,000 parts starts with an LED, and certainly the activity LED on the board here is one of the first things we added when we started this project. So I'd recommend you have a look at the Internet Archive for this if you're trying to understand more about the workings of the Intel 8088, 8086 processor, then that does a good job in covering it. So what I've tried to do in this project is use early 1980s components where possible. However, there are some exceptions. I'm not trying to build a 1981 identical IBM PC. I'm just trying to understand how the PC hardware and software works. So in particular, simplifications using modern static RAM chips over legacy dynamic RAM. And again, Grossblatt says that's a mistake to try and do any more recent project using dynamic RAM. Using modern EEPROMs or EEPROMs over legacy EPROMs. So this just simplifies programming. You don't have to erase things using UV light and things like that. Using programmable logic devices or PLDs, which is something I didn't really know much about before I started this project, but you can use these to simplify logic and decoding. These weren't around in the early 1980s, but by the mid 1980s certainly the compact Desk Pro designs included quite a lot of PLDs. Using 3.5-inch floppy disks rather than 5.25, and a PS2 keyboard and mouse rather than the original PC and PC XT ones. They're difficult to get, but PS2 keyboards and mouse are still fairly generally accessible. And in fact, a lot of USB keyboards with an appropriate adapter will actually still work with a PS2 port. Then for hard disks, I actually am using a 2.5-inch SATA hard disk, so a fairly modern hard disk with a SATA to IDE converter. So this avoids trying to use legacy IDE disks and also any issues with 12-volt power supplies. And finally, for the video is actually producing VGA output at sort of 640 by 400 at 70 Hertz, rather than the original MDA standard, which was a different frequency range. Also the CGA range. Without an original MDA or CGA compatible monitor, then producing video signals for these, it'd be quite awkward. I'm plugging this into a VGA to HDMI converter and then an HDMI video adapter that allows me to capture the output for these videos. So why use the Monochrome display adapter? Why not use CGA, EGA or VGA? Well, we do need PC compatibility for standard PC software to work, and the video card I developed in the Nanocomp 6809 project produced VGA output, but it wasn't register compatible. Now the MDA monochrome display adapter is simpler to develop, and especially if we use dual port video RAM, and the EGA and VGA standards use custom very large scale integration chips for the control registers and a lot of the glue logic. So that would require like 140, 160 pin surface mount devices, and those aren't really practical for breadboards. And the other key thing about the MDA card is it is actually possible for MDA and other video cards to coexist for debugging. So if you don't want to go through the earlier summary videos, then I'll very quickly go through the high-level design here. So these are some block diagrams that I've tended to use to try and explain the various stages of the project. So we started with the Intel 8088 processor. As I said, that's the same as an 8086, apart from it talks to the outside world through 8 data pins rather than 16 data pins, so it makes things simpler. Then we needed to add a clock, reset and a clock circuit and power supervisor circuit. Now the data bus is 8 bits, the address bus is 20 data lines, A0 to A19, so that gives you a 1 megabyte address range. And then there are various control signals, so in particular we've got memory read, memory write, an IO read and IO write. Now the Intel architecture separates the IO devices into a separate address range from the RAM and the memory, whereas the Motorola just used the same address space. So then we need to add a bus controller and some buffers and latches, and these are the things really that the 8088 requires in addition to what the 6809 needed. Then we're adding the address decoder, the ROM, the RAM, and the memory map we started with was just using the Motorola style memory map where the IO ports were just mapped to a higher address range. Then we add the peripheral interface adapter, the LED 7-segment display driver, and the keypad. Then finally we need to add a serial port, and he used one of the FT232RL, fairly cheap £2, £3 USB to serial port converter So that plugs into the PC and we don't have to deal with plus or minus 12 volts for RS-232, etc. So it simplifies things quite a bit. Now the chip that we're using for this originally was the Motorola 6850, and that's actually capable of working quite a bit faster than the original Intel chips that was used on the PC. So this is normally doing about 56 kilobits per second, whereas the original IBM PC serial controller chip can only do 9600 baud. So the keypad and decoder, this comes from the original design, and this is from the Keypad schematic. And these are just some of the things we used to develop the keypad. Now I couldn't really put the keypad on solderless breadboards, so what we ended up doing is using stripboard or veroboard, and the Fritzing software package is actually quite good for designing this. So this is the layout, and you can see the various colors to indicate the connecting lines between the various keys and rows. Then without the keys, then if we look at the 7-segment display, so that helps a lot to design the stripboard. Now, as part of the original Nanocomp 6809 project, one of the reasons why I was able to do that is I did this project back in 1981 when I was at school, and I still have the monitor ROM from the original project, which I bought, I think, from Technomatic in the UK back in the day. So I was able to reverse engineer that, and I'll talk about that in a minute. Now, why do we need a monitor program? Well, the Apple I originally included a monitor called Wasmon, and Ben Eat has done a whole video on that, which again, the videos and links here will all be in the description below if you want to go off and look at those. Tim Patterson, who was the original developer for 86-DOS, which was the predecessor for MS-DOS, apparently the debug.exe, which was shipped with MS-DOS, was originally in ROM, and he used that actually for developing DOS originally. And a lot of the original micros had a basic ROM, so the PETs, BBC Micro, Spectrum, Dragon 32, they all had basic in ROM. Although that wasn't really a monitor, it would allow you to load from tape, save to tape. You could peek and poke memory, and you could do sort of a basic sort of system maintenance things. So the Wasmon is probably the smallest, is less than 255 bytes. Debug.exe does take some learning. It's not the easiest to use program without documentation, but it is actually very powerful. Allows you to read and write boot sectors and all sorts of things. And then finally the Microsoft Basic interpreter, which existed in a lot of the early 1970s, 1980s micros. Now, the Nanocomp Monitor is a very simple operating system. I don't think operating system is really probably the right word. But what it does do is initializes a system stack and interrupt vectors, allows you to inspect and change memory, execute programs, display register values after a breakpoint, and can also load and save memory over the serial port. So this is originally to audio cassette, but in the Nanocomp project I changed this to use the Motorola S record format, which I'll talk about on the next page. Now, the original monitor was actually Motorola 6800 assembly code, and it was updated to work to the 6809 in July 1981. So a lot of it actually is probably not the most efficient 6809 code, but it works. In video number 12 of the original Nanocomp series, I reverse engineered, disassembled with help from links from some work that Mike Spivey did on the Nanocomp 6802 ROM. So I used that to help disassemble that. So then when I was able to build that from source, then it's allowed me to continue to develop that. And we're going to need an 8088 monitor to build and test the hardware and to debug the XT BIOS. So once the BIOS is operational, then we can run MS-DOS and we probably won't really need the monitor. The Nanocomp Monitor is fairly simple. So we have load, save, continue, go, memory inspect and change, register values, and increments. That's used to page through individual memory values. Now, in addition to those original values, what we had to do for the Intel platform, because we had code segments, data segments, and extra segments to worry about because of the 1 megabyte address range, the original 6809 only had a 64K address range. I added a couple of commands. So E allows the extra segment to be set for the memory and the load operation. So just allows us to move around the 1 megabyte memory map without having to do too much changes to the monitor. C allows us to set the code segment, so we can actually change the block of RAM where we're actually executing the code. So when I was developing the BIOS, for example, then I tended to put the BIOS at the 60000 segment so that I could actually change it and load it using the load from serial port SREC. And then most recently I added a B command. All that does is starts the BIOS and executes the BIOS from the monitor. So it just meant that rather than me having to download the monitor every single time in SREC format, I could put it in the ROM and I could inspect memory and do things like that, but then I can also just start up the BIOS. At some point in time I'll get rid of the monitor and it will just go straight to the BIOS. It's the Motorola S record format, so all this is a text record format for sending binary data. There is a Wikipedia page for it. Probably the best thing to do is just show you an example. So this is the S record format for the BIOS, and all it has is a record type. So S1 is primarily what we do, how many bytes are included, the address where this goes. So you'll see this is only a 4-digit address, which is why we needed to set the segment value before we actually loaded this. And then there's a checksum on the end, and in fact Notepad++ will actually tell you whether the checksum is correct or not. So if I change this to a 1, for example, then you would see that you see there that the checksum would then be invalidated if the checksum isn't right. And so this is a fairly large file, about 1,000 odd lines. It's about 77K. And then the last record then is an S9 record, which just basically says this is the end of file. So it's a fairly simple file format, and this has actually worked very well and has been a lot easier. I didn't need to switch to an Intel hex format, which would equally be as valid, but I already had the code to do SREC. Converting 8-bit processor code into 8086 assembly language, there are a few gotchas and things. I wasn't that familiar with 8086 assembly language. The biggest step really is that the use of segment registers. So because this has a 20-bit physical memory address, then in fact the normal addresses we would be thinking of are just 16-bit addresses, 0 to 15, and that covers a 0 to 65535 sort of range. But the segment register then effectively provides the top 4 digits of a 5-digit hex number. And it's a little confusing. Effectively, it's sort of a number times by 16. And all that happens is the CPU adds the lower 15 bits to the upper 15 bits. Effectively, the segment register's rotated by 4 bits upwards, and that comes up with the physical address. I must admit, I only ever tend to set the top 4 bits of the segment register. Just makes it easier to understand. So there's some information here that in the detailed videos I covered conversion of the 6809 to 8088. There isn't an automatic way to do it, but it's actually relatively straightforward to convert the instructions. So that covered the topics for the first summary video. The second summary video really covered the development of the Monochrome display adapter. So this is an image of the Monochrome display adapter. There's the Motorola 6845 video controller chip and the ROM there. Now it actually made up of 66 chips in total, although there was a parallel printer port on the board as well. And this is some of the documentation from the IBM technical documentation, and there was some simplifications here because we were using dual port video RAM that had 2 lots of addresses and 2 lots of data. It meant that we didn't need to include a lot of the multiplexing and gating, and there's some other simplifications. But we also were then using a VGA compatible digital analog converter that's basically producing the output, and that allowed us to produce more flexible colors and make life easier for interfacing with more modern hardware than the original Monochrome and CGA video adapters. So a few changes I had to make. So switch the design from using just the memory addressing to use the I/O ports as well. So now the peripheral interface adapter over here and the serial port are now mapped to an I/O range, pretty much the same addresses. So now it's starting to become more like a PC rather than just the original Nanocomp. Now again, to go through the video display, this is covered in the summary video 2 in more detail. We're using a Motorola 6845 compatible cathode ray tube controller chip, and this produces the horizontal sync, vertical sync, and other control signals for the cursor video output. It makes use of a 25.175 MHz dot clock, so that's the VGA dot clock frequency, and then this is divided down to provide the character clock, which runs around 3.1 MHz. Then this is used to generate the video control signals for the video RAM, and also the CPU can access the video RAM at the same time. The output from each character cell then determines the top addresses for the character generator ROM, and the current row that comes out of the CRTC determines which line of the character. This gets shoved into a shift register, then outputs the individual bits that then controls the video digital analog converter over here. For the MDA, we needed to add a CRT control and status registers. And then the logic that was most complicated was really all the PLDs around controlling the video output. So this was actually all necessary for the foreground, background, blinking, high intensity, etc, etc. So there are a couple of programmable logic devices do all this code, and that was quite tricky to get working properly. But basically all this does is takes the foreground, background out of the shift register here and decides which color it shows for the VGA output here. Now for monochrome, we're using shades of either white and grey or green and dark green, and for color it is actually possible to produce color output very similar to CGA, and the original MDA card apparently could do color with the appropriate monitor being connected. So this is the MDA compatible port layout. We did need to add some additional ports here to set up the video DAC palette here, so this is not quite standard. This video palette is a standard thing to be set up for a VGA graphics card, for example. So this is the output. This is an initial test screen where we're just showing the white and grey and black video output. This is using the green, so this is what we're going to be using for the main MDA output. And then when doing the colours, then this was just the sample of the colours from some of the early tests that I was doing. We also needed to add some fonts, so the URLs and things here is where we're able to download legacy fonts, and we just load those fonts into an EPROM and use that. Then the monochrome display adapter attributes have things like blinking, high intensity, background, and you can see these are all the various combinations for the attribute bit that produce the various things. You obviously can't show blinking here. In the test videos you show the test pattern indicating all the output there. Then as far as the colour, so the left hand side is what the EGA, VGA colours were. CGA colours were a little bit different, in particular brown for CGA, and there's also some work being done to get the accurate colours from measuring voltages off CGA outputs, and so some of this stuff I've fed into this, so hopefully the colour output when running CGA colours, then this is actually pretty accurate. This is the output from the video card and matches pretty closely the lower colours here, which are the colour corrected ones. So that's the end of the second summary. The most recent number of videos, video number 22 to 36, we've really been looking at what makes a micro IBM PC compatible. So this is the slide I showed earlier. So we've already done the video card. So the video card MDA compatible, so that's already there. We need to obviously run some form of MS-DOS, and these other things here are what we need to add to make this computer into PC compatible. When looking at the original diagram here, then these bits in red are not really part of the PC architecture, they're Nanocomp, so we don't really need those to make it PC compatible, so we can remove those at some point in time. So what makes a micro IBM PC compatible? Well, you need to use an Intel 8086 compatible instruction set, and we're using the 8088, which is compatible. You need a BIOS compatible with the IBM PC software interrupts. So if you've got a real mode operating system and a compatible BIOS, then it should work on any computer with the BIOS implemented using that standard. The I/O ports and interrupts generally need to be the same as the PC, or at least the BIOS is configured for the differences so that the higher levels of software like the operating system are not aware. So the PC ISA 8-bit or 16-bit expansion bus. Now in our particular case we can plug in those types of cards, but we don't really need to because we're building on breadboards, but the signals which are made available on the bus will be ISA bus compatible. We need an interrupt controller, which is really needed for the keyboard and floppy disk controller. Timers, the parallel port interface, port B in particular, and speaker output, particularly for the power on self-test beep codes. We do need a direct memory access controller, so that's needed for the floppy disk controller. Some PC clones, so the Tandy 1000 PC Junior didn't include a DMA controller. Theoretically that made floppy disk access more complicated, though my experiences with DMA controllers, I would perhaps argue the point on that one. And then finally a PC compatible keyboard. So this is a diagram of the I/O ports and interrupts that we've been using on the project. So things in red we're not planning to use, green we are using, and orange we'll probably use at some point in time. Now the non-maskable interrupt is actually used for the Nanocomp Monitor abort key. So if we press abort, then it theoretically can go into the register display in the Nanocomp Monitor. And then the I/O ports, again the green ones here are the ones which we're using in these early stages. Orange we will add probably in the third stage of the project, and red at this point in time we don't have plans to use. By making all of these things the same as the IBM PC, then the BIOS doesn't require any changes to accommodate this. So what is a BIOS? So BIOS stands for Basic Input Output System. The first BIOS was really developed, certainly on microcomputers, was developed by Gary Kildell in 1975 for CP/M. And what it does is isolates the operating system, such as CP/M MS-DOS, from the hardware differences. The operating system can work on a fairly standard platform. Normally known as firmware, it is normally in ROM, EPROM, EEPROM or flash memory. Now the IBM PC BIOS supports about 15 software interrupts. Those functions, there's a link there to go off to Wikipedia, which references those. Now, what was unusual is the PC BIOS source code was actually provided with the IBM PC, PC and AT technical reference guides, and clone PCs quite often used Phoenix or Award BIOS, and those are the BIOSes that tend to have the blue setup screens. Now, the Compact Portable developed a cleanroom BIOS. In other words, what happened is the developer who developed the BIOS never saw the code for the IBM BIOS, and the way how they developed it, they got some developers to write the specification from the source code, and then the developer never ever saw the original IBM BIOS. So there was no danger of them ever actually reproducing of the source code. Some of the other BIOS manufacturers weren't quite as clever as that. Now the BIOS provides power on test messages, RAM test and boot failure messages, and normally the BIOS will also try and load initial operating system from floppy disk or from hard disk. So steps we needed to follow to get the BIOS running. So Sergei Kiselev's 8088 BIOS is great, the link there, and his XI XT PC is a design for producing a PC XT compatible on PCBs. So what we had to do for this is create a breadboard PC configuration and configure the options. As I said earlier, I relocated the BIOS code to run in the 60000 range using the extra segment on the Nanocomp Monitor. That allowed me to run the BIOS actually in RAM, so I could change things and modify things without having to burn it to ROM every time. The other things we had to do, I had to reduce the available RAM to 256k, otherwise the BIOS RAM test would actually overwrite itself, and I needed to actually add the extra register configurations for the VGA 640 by 400 output. So the base BIOS would do MDA video timings, which is something like 16 kilohertz line frequency and 50 hertz vertical frequency. So there need to be some modifications there. And also we need to initialize the VGA digital analog converter palette as well. So a few minor additions. And then in order to load the BIOS, all I had to do is to set the extra segment to be 6000, code segment for executing the code to 6000, and then just do go FFF0. And that would actually run the BIOS. When the BIOS is in ROM, then it's always at the top of the memory map because the Intel processors go to FFFF0 to execute the first instruction. So really the 16 down from the top of the memory map. This is the screenshot of when the BIOS was first running, and at this point in time it didn't actually have the hardware in there to detect the difference between the MDA and CGA adapter, so it's coming up as CGA, but in fact later versions will actually show the MDA adapter. So to get the BIOS loaded here is a key step necessary to be able to then start booting an operating system. So one of the other things we needed to do was to add a keyboard. Now IBM PC keyboards have changed through the generations. So the original PC had an 83 key 5-pin DIN, so this is a large circular connector. The XT had a similar one. PC-AT still used the larger 5-pin connector, but it had the enhanced 101, 102 key keyboard, which we would probably recognise today. And then the PS2 range came out, had the enhanced 102 key keyboard with the PS2 6-pin mini DIN. So that would be what most people would recognise as the older style keyboard connector before USB came in, and that's actually what we're using. Nanocomp 689 video 18 included a lot of the background about PC keyboards, which didn't reproduce in the Breadboard PC. We just want a standard 102 key plus keyboard. Basically the PS2 compatible ones are still available. You can buy them for £20–25. And in actual fact, with a USB to PS2 converter, you can use them with most USB keyboards as well. Now, Ben Eater does have 3 videos on the low-level PS2 keyboard operation, so you can have a look at that, and that covers all the details of how the PS2 keyboard communication works. Then we went on to add a direct memory access controller. So DMA, direct memory access, is really dedicated hardware for transferring data between memory and peripherals, such as a floppy disk and hard drive and memory. Now, theoretically, it is possible to do between RAM and RAM, but that's not actually very easy to do on the PC. The Intel 8237A DMA controller, which was used in the original PC and PC-XT, has pretty much been emulated in the chipsets of the 486 processors upward. So even your PC, if you're using one today, will probably have one of these DMA controllers emulated in its chipset deep inside. I know that Intel have been talking about in future generations of processors of removing some of this backward compatibility stuff. Now, the PC-XT ISA bus DMS legacy is different from more recent PCI Express DMA. There is quite a lot of good information on this and this IBM PC and compatible computers chapter 15. One of the original justifications for using DMA is that it was faster than using CPU controlled I/O. So in fact, this book actually includes an example where with CPU code running on 8088 would take 39 cycles per byte, whereas DMA controller would do it in 10 cycles. So theoretically, it would have been about 4 times faster with the original clock CPU at 4.77 megahertz. The irony is that once 286's got to about 20 megahertz, then in fact the programmed I/O or CPU controlled I/O was actually faster. So in fact, DMA really only had a benefit for the first 2 or 3 years, and ever since then it's kind of been a legacy millstone around everyone's neck. Then we added a floppy disk controller and drive. Now, the original PC only supported 5¼ inch drives, initially with only 160 kilobytes per side in DOS 1. Then that was increased to 180k in DOS 2. PC-XT added double-sided drives which could do 360k, and then the PC-80 added the high-density 5¼ inch drives that could do 1.2 megabytes. Then the PS2 and I think the Compact Desk Pro 386 from around 1986 added 3.5 inch drives with 1.44 megabyte capacity, so that's the double-sided high density. There were some 3.5 inch drives I know in some computers like the Apple Mac, Amiga and others earlier than that. There's a document referenced here that includes all of the various MS-DOS supported formats, so it includes all the various parameters. Now, 5¼ inch drives are difficult to get, and floppy disks are probably even harder. Now, I do have a number of 3.5 inch floppy disk drives and 2 new boxes of disks, so you're going to be using the 1.44 meg floppies. And in fact, you do need MS-DOS 3.3 to use 1.44 megabyte floppies. I have been able to get a version of PC-DOS 210 installed on a 1.4 meg floppy disk, but it's a bit of a nasty hack, and it actually is formatted as a 360k floppy disk. And certainly if you try and do any drive checking with any modern operating system or win imaging or anything like that, it complains about the format, but it appears to work. So here's the diagram from the original IBM XT floppy disk controller. All of the IBM PCs and compatibles actually use this NEC floppy disk controller. It's known as the NEC PD765. So all the registers and commands are all compatible with this. And the original PC just had a status port, a data port and a digital output register. Now when the higher capacity drives got added, then there were a couple of extra ports got added for controlling the data density and for detecting drive change. And you can see here in the various registers here that the bits on the output register controlled the various drive motors. The original controller could do up to, I think, 4 floppy disks from the one controller. All floppy disk controllers are register compatible generally with this NEC controller. Quite often the later floppy disk controllers like the Intel 82077 are actually embedded in PC chipsets, so certainly from the early 90s onwards you'll find that a lot of the disk controllers and DMA controllers are actually embedded in the chipsets which are used in modern PCs. Now the particular chip we're going to use for our floppy disk controller is a Western Digital 37C65, and it provides all the hardware needed for the floppy disk controller except for the address decoding. Now the only issue I did find is that the 40-pin DIP package, which is like breadboard friendly, does exclude the disk change pin, and so this did actually cause me a problem which I'm going to have to address in a future video. And it uses the 34-pin, so that's 2x17 floppy disk cable, and I built a strip board DIP connector for the breadboard. There is a design here which I based this on the Raspberry Pi design from Scott Baker. The links will be in the description below. And these are the registers. So these are the registers I discussed previously, and these are the new ones that are added in later versions of the drives, particularly the higher density drives I think added these. And the main issue really is that the BIOS here, the disk change bit, I needed to hardwire some code in there until such time as I sort out how to get the signal from the floppy disk drive to the BIOS. And this just shows that on the cables I've got that come from an old Dell desktop, then the cables are keyed in fact, so you can only plug the cable into the disk controller and the cable into the floppy disk because different pins are keyed. Floppy disk cables are a little confusing, and quite often they have reversed cable twists. Most floppy disk drives are actually shipped as drive B, or the second drive, and then the twist actually turns them into floppy drive A. So that's one of the things I discovered in trying to do this. So just be aware if you're doing this about drive A and drive B and the twisted floppy disk cables. Now the Breadboard PC Memory Map, at the highest level we've got the first 512K is system RAM, then there's a bit of a gap, and then we have the video RAM for the Monochrome display adapter, and then the BIOS actually goes from F8000 up to the top of the memory, so that is a 32K chunk. Now the Intel hardware, and particularly the 8088 and 8086, look at the top FFFF0 for the first instruction, and normally that will include a 3-byte jump instruction to go to wherever else you want it then to start executing on that. Later versions of processors still use the top of memory, but it would be 32-bit or 64-bit. Now in a lower area of memory, the first 1000 bytes is actually assigned to the processor itself. This provides interrupt vectors, so it provides 2 bytes for the segment and 2 bytes for the instruction pointer. Now in fact, because most of the interrupts above about, well, most of the interrupts are used below about 64, so in fact the BIOS by default sets the stack at 400 initially and works downwards. So theoretically, if you're ever using some of the higher interrupts like 250 and things like that, you would get corrupted by the BIOS stack, but luckily only about the first 20 to 50 or so are used generally on the PCs. Then at 400 upwards is the BIOS data area, so this is where a lot of the working storage information is stored. When the PC boots up, what actually happens is the boot sector on the floppy disk gets loaded at 7C00. So you'll see in some of the later videos 7C00 appear quite a bit, and that's where floppy disk boot record gets loaded and then executed. And what that then does is loads the root directory sector at 500, checks to see whether the IBM bio.com and IBM DOS.com were the first 2 files on the disk, or for MS-DOS it's io.sys and ms-dos.sys. And then what it will do is to load the IBM bio or io.sys from 700 and then start executing from there, and then that will actually load the IBM DOS or ms-dos.sys, and then the operating system then loads from there. So again, when looking at the logic analyzers when trying to diagnose PC booting and things, then you'll quite often see the 500 means it's the root directory, 700 means it's the DOS BIOS layer, and 7C00 is the boot sector. So when you switch on your PC, what actually happens? Well, the first thing that happens obviously is that the Intel processor looks at the top of memory and looks to see where the first instruction it should execute. Now in the ROM for the BIOS, then that actually goes from the top of the BIOS and then jumps down into the middle. I think there's a section called cold start. What it has to do initially is to initialize the parallel port interface and set up things so you can get the beep code. So if there's any memory problems and things like that, then you'll get a beep code first. Sends stuff to the power and self-test register, initializes a DMA controller, the programmable interrupt controllers get initialized, then the timer, initializing the PIC, then the keyboard controller, works out what the video mode is, tries to detect if there's any video BIOSes loaded on any video cards, initializes a video, initializes the real-time clock, and if there's any CMOS, checks the checksum on that, tries to detect the serial, parallel, floppy disk ports, detects the RAM and tests the RAM, Then it looks to see if there's any extension ROMs anywhere. So this would be things like network cards or SCSI cards, for example. And it's generally looking for the magic word 55AA or AA55, which it looks for to determine whether those exist. Then it looks to boot the OS, so it looks to see if there's anything for setup. So do we need to set up the CMOS? And then it tries to then load the boot sector from the floppy disk. And if it doesn't do that, then it will go around and retry a few times. So that's what happens when you switch on a PC, and even modern PCs with the legacy BIOS mode enabled, then it will be going through something very similar to this. In actual fact, to boot the PC, what happens is the BIOS does software interrupt 19 to boot the OS, and on the XI8088 BIOS there's actually an IPL routine, initial program load. And what this actually does is it tries in a loop at least 4 times to load from the floppy disk. It resets the floppy disk system, gets some parameters and things. What it then will do, if there's at least one floppy disk drive, it'll try and read the 512 byte sector for head 0, drive 0, track 0, sector 1, and it puts that in 7C00 via DMA. Once that's been loaded in there, it checks to see whether the end of that sector has the magic number, so AA55, and then if that's successful, it jumps to 7C00, and that should hopefully start the operating system. Now I should also say the floppy disk boot record is different from the hard disk boot record. Floppy disk boot record is specific to the operating system. The hard disk master boot record could actually allow you to select multiple operating systems. So then the floppy disk boot record, there is a detailed explanation of this for MS-DOS 5 at starmanpcministry.com, but I won't go through the details of this at the moment. They'll do a later video on that, but needless to say, in trying to work out why things don't work, you need to go into the details of exactly what happens when you start things up. And this is actually what a boot record looks like. So the first 2 instructions here actually say jump to a little bit further on in the code, and there's actually an area of data here specific to the floppy disk configuration parameter block there, and you can see down the bottom there's various messages and things, and there's also the file names that the boot sector looks for to see whether you've got a valid operating system. This is a diagram similar to what was on the Starman PC Ministry, and all I've done is done this for MS-DOS 3.3 rather than MS-DOS 5. So you can see here the first 2 instructions here jump to the code over here, and then we've got OEM label here, so we've got MS-DOS 3.3, and might have IBM DOS, for example, IBM 2.0 I think. The BIOS parameter block includes information about the floppy disk. Then we've actually got the code that actually starts up the operating system, the error messages, and then the root directory file names, and finally the magic bytes. Now in later versions of MS-DOS I think these checks were removed, but certainly in the versions we're looking at here, if you don't have those bytes at the end, then it won't be a valid boot sector. Then finally we went through building DOS4 from source. The reason for doing that really was to understand exactly how all this works, and the last couple of videos we've built DOS4 from source and addressed some of the issues with the source code that was released, and this has allowed me to build my own MS-DOS 4 io.sys, ms.sys, and we've shown previously that we've been able to actually get quite a lot of diagnostic messages coming out for doing this. I'm going to continue to do this, and this will help to hopefully sort out the last few issues and things I have in booting higher versions of DOS. So at the moment MS-DOS 3.3 and 4.0 aren't quite booting properly, so hopefully I'll get to the bottom of it with this information. And whilst I was doing this, I did come across an actual issue in the BIOS, in fact, in that as this was coming up, it actually got stuck at the bottom and the whole PC froze. What it's actually caused by, actually the BIOS itself had the video driver code that only really supported CGA, or if you had MDA and CGA installed together, but if you had MDA on its own, then basically it would hang forever. So there were some fixes and things we needed to do this. So really that summarises where we've got to so far. So this sort of summary really covers everything leading on after video 21 and covers really the whole project. And what I will be doing in future videos, I'm going to be doing a little bit more work to try and sort out getting MS-DOS 4, 5 and later versions booting properly. And then we're going to be going on to see if we can actually build a very basic Windows PC. So this will be running Windows 2 probably, possibly Windows 3 if we can get it working. So thanks for watching. If you don't want to miss out on future videos, please hit subscribe, and if you could hit like, it just helps to make the videos appear to a wider number of people. All of the links and playlists that I've mentioned will be in the description below the video. Thanks for watching.